This is the Northrop Grumman B-12 Spirit, simply the most expensive airplane in the world. Each unit costs $2 billion, including the spare parts. In fact, the B-12 construction program was one of the most complex and expensive programs in all of history. It cost just over $45 billion, almost twice what the Apollo program cost, which aimed to take man to the moon. But beyond its unusual shape, you notice something different about it. This plane doesn't have a fuselage or tail stabilizers, which is that vertical wing you find on basically every plane. And as physics teaches us very well, a plane can't fly without a tail stabilizer. And we have two major accidents involving the total loss of this component. American Airlines Flight 587, in which due to successive and exaggerated movements by the pilot in operating the tail stabilizer, it ended up being torn off in mid-flight, and the aircraft immediately began a rapid dive toward the ground. And Japan Airlines Flight 123, in which, due to a maintenance error on the bulkhead, it ended up exploding in mid-flight, taking with it a large part of the tail stabilizer. The aircraft became uncontrollable and, despite the pilot's efforts, crashed into a mountain. But as we can see, the B-2 Spirit not only takes off, but also flies perfectly, even without a tail stabilizer. But how did its designers achieve that? In the 1960s, thanks to extremely complex work related to the physics of radar waves, proposed by the Soviet physicist and mathematician Pyotr Ufimtsev, concepts like the finite cylinder with flat bases, the finite cone, the finite paraboloid, the finite thin wire, and the finite flat plate, they were already very well explored, mainly for military applications, especially in stealth applications. The one in which large objects like a Boeing 737 or even a Boeing 747 could theoretically appear on the screens of the world's most advanced radars in very small sizes, like those of a small bird or even an insect. And this was proven with the super-secret bomber, the Lockheed F-117 Nighthawk, a 20-meter-long plane weighing just over 13 tons, but it has a radar cross-section of only 0.001 square meters. In other words, it appears on radar screens as small as a little bird. Even though it's a 20-meter-long plane, these same principles guided the design of the B-2 Spirit. But the B-2 was being designed to be the main bomber of the United States. In other words, it had to be a much larger and much more capable bomber. But it absolutely had to be much more invisible than the F-117. Barely visible like an insect, even on the world's most advanced radar screens. And that forced the engineers at Northrop Grumman to choose the flying wing design. A much more subtle and discreet design. The plane's fuselage would flow naturally from the wings and lack tail stabilizers. Despite their benefits, they greatly increased the plane's visibility to radar. But this turned out to be an extremely complex task and created a dozen other problems, among which the main one is that the aircraft would be extremely unstable in flight, since the tail stabilizers are an extremely important part for the stable flight of any aircraft. They are present on everything from fighter jets and private jets to commercial passenger transport planes. But then, how did the engineers manage to make the B-2 Spirit a perfectly stable aircraft even without tail stabilizers? The answer to this question is found at the rear on the tips of both wings of the B-2 Spirit. If we look closely during flight, you can see there are some surfaces that are constantly partially open throughout the entire flight. These surfaces are called split rudders, and they are responsible for maintaining the B-2's overall stability during flight. But to really understand how they work, we first need to understand how stabilization happens in a conventional airplane. In a conventional airplane, there are three sets of wings, starting with the main ones, which are also the largest, and are located in the center of the airplane. These, besides providing lift, which is the force that keeps the airplane flying, also carry most of the weight of the entire airplane during flight. Because they're in the plane's center, creating a symmetry of forces. At the tips of each wing, with the action of the ailerons, the airplane is able to perform rolling movements along the longitudinal axis. But let's say the nose was heavier compared to the tail. This tendency cannot be canceled out, since the wings in the center can't generate any force to counteract this tendency. And that's where the rear wings come in, also called horizontal stabilizers. These wings, besides carrying a small portion of the aircraft's weight, have elevators at the rear of each wing that allow the plane to make pitching movements. In other words, movements of the nose going up and down along the lateral axis. But even so, the plane is still unstable on the vertical axis. If a crosswind hits the tail, the aircraft will tend to skid or yaw, as this movement is known. That's where the vertical stabilizer helps, which is the wing that stands upright on the tail. It stabilizes the plane on the vertical axis, preventing forces that hit the plane from the side, like the wind, from making the plane skid or yaw. But since the B-2 Spirit doesn't have a vertical stabilizer, it would be unstable on the vertical axis and would naturally have a tendency to yaw or skid to either side. To avoid this, the B-2 relies on a principle called differential drag, in which the drag generated by one of the wings can be increased or reduced to keep the plane stabilized. If the dozens of computers and dedicated systems detect that the plane is becoming unbalanced to either side, and the component responsible for doing this job is the split rudders, which are located at the tip of each wing. These split rudders are a set surfaces where one opens upward and the other downward. They can reach a maximum angle close to 90 degrees. And they are the most critical and most important part of the B-2 Spirit in terms of safety and stability during flight, because without them, the B-2 can't remain stable in flight. And they work in the following way. As soon as the computers detect that the B-2 is losing balance, for example, with a tendency to roll to the right, the computers
imediatamente abrem esses split rudders da asa esquerda,
greatly increasing drag on that wing compared to the other, where the split rudders are nearly closed, restoring the plane's balance. And if the plane has a tendency to roll to the left, the computers immediately open the split rudders on the right wing, increasing its drag and bringing the plane back into balance. This happens fully autonomously, thousands of times per flight, without pilots noticing the corrections. And during landings and takeoffs, these split rudders play an even more important role. Due to the low speed of the aircraft and the low airflow over the wings at these moments, they need to be much more open to generate significant drag to keep the aircraft stable, as you can see in the video. And after landing, they are fully opened, acting as aerodynamic brakes, helping to slow down the aircraft along with the brakes on the wheels. But like the B-2 Spirit, advanced, there is a second system that works simultaneously with the split rudders, which is the B-2 Spirit's 4-engine power symmetry system. It basically follows the same principle. However, it relies on the power of the 4 engines. So as soon as the B-2 starts to yaw to the right, the engines on the right wing are throttled down to a lower power than those on the left, helping bring the plane back into balance. And if it is,
na para a esquerda, os motores da asa esquerda são desacelerados a uma potência menor que os
right, helping the plane regain balance. And this system is also used during turns, following the same principle. This system plays a crucial role during B-2 Spirit missions, since the opening of the split rudders greatly increases the B-2's visibility to radar. And that's why, when the B-2 is on a mission, the action of the split rudders is limited, with the maximum opening angle greatly reduced.
Ok, mas para curvas, como o B-2 Spirit?
Stripe. Again, the answer is found on its rear. To make it turn, the B-2 has what are called elevons. It's a mix of elevators and ailerons. There are 6 elevons on the B-2 Spirit 3 on each wing, but apparently only the elevons closest to the center of the plane on each wing are used in tight turns, as you can see in this video. Since the turn is to the right, the 11 on the right wing goes up, while the one on the left goes down. If it turned left, the opposite would occur. And to see how these systems complement each other and work together, at the precise moment the turn is commanded, the elevon rises, and at the same time the rudders on the same wing open, helping to stabilize the airplane during the turn. This happens at the same time that the engines on the left wing are probably slowed down a little.
Em relação aos da direita. Esses sistemas são tão incríveis.
Complex systems work so well and play such a critical role in the flight of the B-2. If they stopped working mid-flight, it would instantly crash the B-2 Spirit. Just a reminder, my name is Aaron Hay. This barely covers all there is to say about the B-2 Spirit's stability. After all, a lot of things are not public knowledge or are highly classified.